Hello, class. Today we are going to explain behavior of gases through relationships of pressure, volume, temperature, and moles of gas. We're also going to convert measurements to appropriate units for gas law problems. For this assignment, you will need the gases note sheet. First, we're going to discuss kinetic molecular theory. The kinetic molecular theory of gases has 5 main ideas. The first states that the volume of the gas particles is negligible compared to the space between the particles. Therefore, the volume of a gas is mostly empty space. What that means is that we really don't count the volume of the particles themselves. We only measure the space between the particles. We know gases have the ability to expand, so they will expand to fit the shape of whatever container they are in. We also know that gas particles are in constant, rapid motion in random directions. When it comes to contact that these particles have with each other, we know that the collisions between gas particles are elastic collisions. We also know that the collisions particles have with the walls of containers are elastic collisions. This means that no energy, no kinetic energy specifically, is lost in the collision process. We also know that there are no attractive forces or repulsive forces between gas particles. We know in the real world, yes, all things experience intermolecular forces. The situations we're talking about for kinetic molecular theory are considered ideal, and you're going to hear that term a lot. We're going to be looking at ideal conditions versus real conditions. So the good news is, whenever we're talking ideal conditions, we don't have to worry about intermolecular forces. The last main idea is that the average kinetic energy of gas particles is dependent on the Kelvin temperature of the gas. Previously, we've discussed the different relationships between the 4 gas variables of volume, temperature, pressure, and moles of gas. We talked about 4 laws: Gay-Lussac's law, Boyle's law, Avogadro's law, and Charles' law. Today, I just wanted to briefly review those, give some clarification on what we've previously observed, and also give you the equations for these particular laws. We are not going to do any quantitative math problems with these particular equations, but if you're going to AP Chem in the future, you will need to know them and you will need to know how to use them. So I'm giving them to you now so that you have them. We also will need the equations to help us figure out a 5th relationship called the combined gas law, which we're going to look at in a little bit. The first relationship, which measured temperature and pressure while holding volume and moles of gas constant, is Gay-Lussac's law. It is directly proportional, meaning when one increases, the other increases. The equation for this is P1 over T1, which is the initial pressure and initial temperature, and that's equal to P2 over T2, which is the new pressure, new temperature. Increasing the temperature results in higher speed of gas particles. This results in more frequent and more forceful collisions with the walls of the container, which increases our pressure. For Boyle's law, we looked at the relationship between pressure and volume. This is the only indirect or inverse relationship. When pressure goes up, volume goes down. When volume goes up, pressure goes down. The equation for this is P1 times V1 equals P2 times V2. By decreasing the volume of a container, we compress our sample of gas, and that forces the particles closer together. Since they have less space to move around, there will be more frequent collisions with the wall of the container, thus increasing the pressure. For Charles' law, we're looking at the relationship between temperature, the average kinetic energy of our sample, and its volume. This is another direct relationship. By increasing the temperature, we know we increase the average kinetic energy. This causes more frequent collisions to push on the walls of our flexible container, and the container will expand to accommodate these extra collisions so that pressure can be maintained constant. This results in a larger volume. A similar thing happens in Avogadro's law when we increase the amount of gas. By increasing the amount of gas, we cause more collisions with the walls of our container, but since we're trying to keep pressure constant, the volume must expand to accommodate more gas. If we were to release some of that gas, then the volume of the container would get smaller, just like inflating and deflating a balloon. The relationship here is V1 over N1, N being the number of moles of gas. You'll see that variable again later, and that's equal to V2 over N2. So one thing we have to ask ourselves among our simple gas law relationships, every single time we held two variables constant. What happens if we can't keep two of the variables constant? What happens if we can only keep one constant, or we can't keep any of them constant? We needed a way to measure these relationships. You'll notice here that one thing always remained constant with the first three relationships we looked at. The moles of gas, or the amount of gas, stayed the same. We're going to use that idea to try and make one single combined gas law that has the other three variables. This way we can account for changes in all three variables at one time. So what we want to do, we know that moles is constant, so we're going to set our equation equal to N, the number of moles. We need to look at our the other three relationships and try and figure out how we can arrange the three variables. This line here is my fraction. So if I look at similarities here, I see both of these have temperature in the denominator. I would say it's probably a safe bet that we can put temperature in the denominator here as well. The other two variables are pressure and volume, which we know are in the numerator. What happens if we combine these two? We get a relationship P1 times V1 over T1. Let's see if that works. If I decided to hold my volume constant, I get my original Gay-Lussac's law of pressure and temperature. If I decided to hold pressure constant, I get my original volume over temperature for Charles' law. And if I hold temperature constant, I get my Boyle's law, P1 times V1. And all of this is going to be set equal to the moles of gas. So we're going to create a combined gas law from this scenario. Since P1 times V1 is equal to T1 is a constant, P1 times V1 over T1 is equal to a constant, we can then have a set of initial conditions set equal to a new set of conditions. The combined gas law is P1 times V1 over T1 equal to P2 times V2 over T2. Again, some conditions for here. You must have the moles of gas constant, temperature must be in Kelvin, and you would use cross multiplication to solve. Again, there will not be any math problems that you will have to solve in this course for this particular equation, but it is something you'll need for AP if you choose to do so later on down the line. The last portion of this lesson today, we're going to spend looking at the different units and how to convert them. In gas law problems, temperature should always be in Kelvin. Remember that Kelvin is a scale that allows us to measure the average kinetic energy of our gas, and it's directly proportional to that. We can't use the Kelvin scale. In order to convert from Celsius to Kelvin, you just need to add 273. So let's do a few of those real quick. Gotta pull up my calculator here, just in case, because we're gonna need it for later. I start with 100 degrees Celsius, and again, I just add 273. So I end up with 373 Kelvin. If I'm going the opposite direction, 298 Kelvin minus 273 would get me my original Celsius temperature, 25 degrees Celsius. Now go through and practice converting the last three in this table. For volume, it depends on which type of law you are trying to solve. If we're looking at our simple gas laws, the ones I showed you on previous pages, Charles, Boyle's, Gay-Lussac's law, volume must be in the same unit on both sides of the equation. Essentially, it should be consistent. Both sides can be milliliters, both sides can be liters. As long as they are consistent, you will be able to solve them correctly. However, when we're using the ideal gas law, as we'll learn in the next lesson, volume should always be in liters. So we've got a few conversion factors here to help us convert between milliliters and liters, which we've had plenty of practice with before. We also have another conversion factor. 1 milliliter is equal to 1 cubic centimeter. Now, cubic centimeter here I represent as cm cubed, but you might be more familiar with this terminology, cc's. If you are someone that is looking to go into the health field, maybe whenever they're delivering a dosage of medicine, they refer to it as this many cc's. All they're talking about is cubic centimeters or milliliters of the medication they're delivering. So you'll need to know that conversion just for life if you plan on going into the medical field. For conversions, just like we did before, you can use dimensional analysis. So my first problem, I've got 1.5 liters. If I started with liters, then liters must be on the bottom, and I end up with milliliters on top. 1.5 times the top, 1.5 times 1,000 is 1,500, and I end up with 1,500 ml. Now, since 1 milliliter is equal to 1 cubic centimeter, I also have 1,500 cubic centimeters. If I'm going the other way, 300 milliliters, I would put the 1,000 milliliters on the bottom, 1 liter on top, and this time 300 times 1 divided by 1,000 gets me 0.3. So I end up with 0.3 liters. And then again, I shouldn't have to do the conversion for centimeters cubed, but it's there in case we need it. All right. Take a moment and pause and complete the rest of those volume conversion problems. We're saving the best for last. Pressure. Pressure has a ton of different units. Atmospheric pressure is the pressure due to the air. The standard, when we're referring to atmospheric pressure, is 1.0 atmospheres. We know that when we go to lower elevations like sea level, we have an increase in pressure. When we go to higher elevations like the mountains, we have a decrease in pressure. That's why sometimes if you're driving in the mountains, your ears will pop because of a pressure imbalance due to the air pressure. We also have standard temperature and pressure, or STP. These are values that we will use when we're talking about the ideal gas law. That is 273 Kelvin and 1.0 atmospheres. And then our conversion factors. 1 atmosphere is equal to 760 mmHg, which is millimeters of mercury. Hg is the element mercury. That particular conversion is used for barometric pressure. Whenever they're looking at the weather, they measure in terms of barometric pressure, and they measure the height, or previously they measured the height of mercury in a barometer. And so they measured it in millimeters, sometimes inches, but millimeters of mercury is common. This is also equal to another unit called torr. They have the same amount, 760 millimeters of mercury or 760 torr, same thing. And then the last one, kPa, kilopascal. All right. So we have kilopascal and then millimeters of mercury. And that's, ooh, I can't spell mercury. Oops. Millimeters of mercury, which is mmHg. So to convert these problems, again, dimensional analysis is what we need. If I'm given 350 torr and I want to convert to atmospheres, I can put 760 torr on the bottom, and I know 1 atmosphere can go on top. So I'm going to multiply here. So 350 times 1, because times the top, divided by the bottom, 760. And I get 0.46, I guess we could round up to 1. My answer of 0.461 atmospheres, ATM. If I'm trying to convert to kilopascals, I can still put 760 torr on the bottom, but I need to use 101.3 kPa on top. So again, we multiply that by the top. So 350 times 101.3, and then divide by the bottom, 760. And I end up with 46.65 kPa. So you can use that as your method of conversion, whether you're going to kPa or to atmospheres. If you're starting in atmospheres and going the other way, again, just pay attention to your units. Whatever you start with needs to be on the bottom so it cancels out. Whatever you end with needs to be on top. We have this chart here. Plenty of pressure conversion practice. We're going to become champs at this. Go through and convert to the other 3 values. Just some clarification. There are 5 separate problems here, so you're converting and inputting values across here. So in this first one, if I've got 1.02 atmospheres, 1 atmosphere on the bottom, times 101.3 kPa on top, and then I just need to multiply. So I multiply by the top divided by the bottom, 103.3 kPa. It's good to write your units. If I was trying to do with torr, 1 atmosphere times 760 torr divided by 1 atmosphere gets me 775.2 torr. And then the nice thing is this last column is going to be the same as whatever your torr column is. 775.2 millimeters of mercury. Okay, go ahead and try the rest of this conversion, and then you can check your answers at the end. Have a good day.